Howdy, and welcome to Constant Velocity Motion, which is just lab number 1 for Physics 2211. Our table of contents, we're going to first be discussing some basic laws of physics and assumptions we're going to make about the lab, and then we'll get into the meat of it later. So first of all, we need to understand two fundamental formulas of motion. Firstly being Newton's second law, which is probably the most important in this lab, and secondarily, the change in position kinematic equation, which is just your final position being equivalent to your initial position times average velocity times time, which just makes sense from a logical perspective. This one, however, is essential to understanding what constant velocity even is and how we can utilize it from a mathematical perspective. To understand it, we need to utilize force body diagrams, which are just a way of showing forces applied on an object in certain directions. As you can see here, these are going in the four normal directions, which is applied friction, normal, and gravity. So, in a force body diagram, we can understand that if an object has an imbalanced amount of force coming in either direction, let's say this one's larger than this value, that means it's going to start changing its momentum in that direction, meaning that its velocity is not going to stay constant. So we need to make sure that doesn't happen. How do we do that? Our net force is equivalent to 0. So we can prove that using Newton's second law mathematically. So we know that our net force times time is equivalent to our change in momentum as shown in this original equation. Manipulating change in momentum into its original form, we have Pf minus Pi is equivalent to this, right? This is just delta P rewritten. If we solve for the final momentum, which is basically what we need to do because we need to solve for final velocity, we can divide the whole equation by mass, but momentum is just known as mass times velocity. Therefore, we will come to this pretty familiar equation, which we also account for Newton's second law. That being said, we also end up multiplying F net by 0, as we previously discussed up here, in order to cancel out the equation to show that your final velocity is going to be equal to your initial velocity, right? Which is incredibly essential to understand for this lab. So, moving on to the meat of the lab, you can see that this is the object that I used in quote-unquote constant velocity, since it's very difficult to find in real life. I found it in the lab, and you can see that its data values are being compiled as of right here. That's important to understand because we put them in a Excel file right here so we can graph them analytically. The problem is we need to compare it to a computational model. So let's look at that. We need to figure out some things for this computational model before we can write it properly. What's our time? What's our initial velocity? How do we update those accordingly for code? Well, let's do that. First, we need to find the initial velocity and the time so we can find those two constants. Well, time's pretty easy to find. It's 1.32 seconds. Why? Because that's how long the object was moving in the video we had originally. That just makes logical sense. However, with velocity, it's a little more complicated. We know since our initial velocity is equivalent to our final velocity and vice versa, that means that our velocity, no matter at what position, is always equivalent to our average velocity, which we know the formula for is just change in position over change in time. And guess what? We have positions and we have times. So after calculating that, we end up with an average velocity of 1.5 meters per second, which is pretty standard. So after putting that in right about here for our initial velocity and our time being 1.32, we can use this formula, which is just final velocity is equivalent to initial velocity, which we discussed right up here, and our position update formula, which is RF equals RI plus your velocity times time, which we discussed up here. You're left with a computational model that does this, which does the exact same thing as the code. You can see it's graphed and it has data values that are also outputted. Boom, we can put them in here. Now we have something to compare it to and graph it, which means we're left with this. Now, the blue is the observed and the X is the computed. You can tell that because the blue one looks a lot worse than the computed one. That's because most of the errors are coming from human errors. So the reason these two graphs don't look identical to each other is because of human error. So this little disjunction right here is probably because I'm a bit of butterfingers and misclicked on tracker whenever I was measuring the velocity of the object in its change in position. The other thing you might notice is that they start at different areas. That's probably because I miscoded and led to an error in which I set the initial position equal to 0, 0, when in reality it probably started at a different x coordinate in tracker. So those are the two errors and why these, but generally they look about similar with the same slope of about 1.5 because that's change in position over change in time. So let's get to our end analysis. What ifs? What if the axes were flipped? Well, it's pretty easy to understand. It's how you flip a line in slope anyways. If we changed our x values, the whole thing would turn negative. And if we changed our y values, the whole thing would also turn negative, just in two completely different ways. You can see this based off this coordinate graph here. Lastly, what does it even mean? When we assume our net forces are equal to 0, that means, can we really determine the number of pushes and pulls on an object? Technically, yes, but that's because that number is infinity, if you consider infinity a number. Most people don't, so I would say no. The reason is because everything exerts gravitational pull on each other. Every single object, no matter how far away it is and no matter how strong their gravitational force is. Meaning there's a legitimately infinite amount of objects exerting a force and a push and a pull on an object at any time. With that in mind, that ends up meaning that you're going to be unable to calculate force effectively, alongside constant velocity motion, or net force, being very difficult to replicate in anything short of an industrial grade lab. That's all I have. Thank you for your time, and goodbye.